Hello, good afternoon everybody. It is lecture number 11 from modern control theory. In this lecture, we would be discussing about diagonalization of matrix, calculation of state transition matrix using diagonalization method, calculation of state space model using diagonalization. In diagonalization, what happens? We can convert by using diagonalization method a non-diagonal matrix system matrix A to a diagonal matrix. As far as applications is concerned of this method, it can be used for modeling of the systems, state transition matrix, controllability, evolution of controllability and observability, and thereafter the controller design as well. So if your system is defined by x dot t equal to axt with the initial conditions x naught equal to x naught, then xt solution of this state space model xt equal to e की power et x0 as we have discussed in previous lectures. So here e raised to at is called as state transition matrix. It is sometimes represented by phi t as well and called as resolvent matrix. So our objective is to determine the value of EAT using diagonalization method. So if you are using diagonalization method, then how you would be able to determine the value of EAT? So in case of the value of e raised to at, that is the state transition matrix using diagonalization method can be determined by transforming the one state to another state. So here our state is xt and a new state zt would be there. So how this xt is related to zt? It should be, since it is a matrix format, xt is a column matrix, zt would again be a column matrix. So there should be a matrix M. This M is called as model matrix and is calculated by using the eigenvectors, and eigenvectors in turn are calculated using the eigenvalues of system matrix A. So once you have defined that xt is related to zt, that is xt equal to mzt, then you can transform your state space model in terms of z dot t. So zt is equal to, from here zt is equal to m inverse xt. If you are taking first derivative of both of the sides, then z dot t is equal to m inverse x dot t. X dot t we have defined state equation as axt, so you can write axt. This xt is defined as mzt, then replace xt by mzt. So here what you are observing, it is another matrix z dot t equal to m inverse am zt. This m inverse am resultant matrix is represented by a bar and would be a diagonal matrix, system matrix A for z dot t equal to a bar zt. So this diagonal matrix, which would be having the eigenvalues of matrix A, and its form would be lambda 1, lambda 2, lambda 3 on the diagonal as the diagonal elements of the system matrix A bar, which is obtained using the diagonalization method. So here the main thing is to determine the value of m. In turn, you can calculate the value of m inverse. Simply multiply m inverse into a into m and you would be getting the diagonal matrix for new state space model z dot t equal to a bar zt. So its solution would be equal to zt equal to e a bar t z0. Similarly, as in case of xt equal to e raised to 80 x0. So this is the solution. So initially what we would be, if we are defining this E a bar t state transition matrix, then its expression would be I, that is the identity matrix, plus a bar t plus a bar square t square over factorial 2 plus a bar cube t bar t cube over factorial 3 plus so on and up to the order of the system matrix A. EA bar t, if you would be putting the values of these one identity matrix A bar t, A bar square t square and so on. So E A bar t would be equal to, by adding these elements, you would be finding this one, this one, this one, and other elements would be 0. So E A bar t can be defined as the elements e raised to a bar lambda 1 t, e raised to lambda 2 t, e raised to lambda 3 t. Lambda 1, lambda 2, lambda 3 or up to the order of the system are the eigenvalues of system matrix A. So in this way you will be able to determine the state transition matrix, or more specifically it will be a diagonal state transition matrix using diagonalization method. Now, however, our purpose is to determine the value of state transition matrix of system A. This was of the system which was converted to diagonal form, but our aim is to calculate the value of e raised to at. So xt is equal to mz, zt equal to this e raised to at z0. Xt would become m into zt, put the value of this e raised to a bar t z0. x0, since x0 is equal to xt equal to mzt, so put t equal to 0, you would be getting x0 equal to mz0. So mz0 equal to m inverse x0. So in place of z0 you can put m inverse z x0. So xt would be equal to m this factor into z0, does mean this factor. So m e raised to a bar t z0 equal to m e raised to a bar t m inverse x0. So this is the factor or combination of matrices m into e raised to a bar t into m inverse, which is called as or reflects as e raised to et. If you would be comparing the equation to the original one, xt is equal to e raised to at into x0. So e raised to at, that is the state transition matrix, is equal to m e a bar t into m inverse. So here you can also write e a t equal to m into the diagonal elements would be having e lambda 1 t, e lambda 2 t, e raised to lambda 3 t into m inverse. So this is the way how we would be able to calculate the value of state transition matrix using diagonalization matrix method. From here, it seems to be tedious and cumbersome to compute the value of a state transition matrix, but as far as the research is concerned, it is useful to have correlation in between the states of the system and eigenvalue of it. So, however, we would not be preferring to calculate the state transition matrix because you would be getting much simpler method using Laplace transform. So why would you be going, instead you are asked to do so? Therefore, but if you are dealing with the research and you are in need to have correlation in between the states of the system and its eigenvalues, then this method is appropriate or useful. Now, take one example. If a system is defined by system matrix A as this one, then you are asked to calculate the state transition matrix using diagonalization. So ultimately you have to calculate m e raised to lambda 1t, e raised to lambda 2t, e raised to lambda 3t. These all elements are based on the eigenvalues. So you have to calculate the eigenvalue. M, once you determine the m, you can calculate the value of m inverse, and in this way you would be able to determine the state transition matrix. It's so simple. And what is M? This is the model matrix. Its elements, column elements, are based on the eigenvalues, and those are the eigenvectors. So initially you have to calculate the eigenvalues related to the system matrix A, and it's very much easy to determine eigenvalues by modulo of determinant of A minus lambda I equal to 0. Using this expression, you would be getting lambda 1 equal to minus 1, lambda 2 equal to minus 2, lambda 3 equal to minus 3. So third order system is there. 3 values of roots are there. Lambda 1 equal to minus 1, lambda 2 equal to minus 2, and 3 equal to minus 3. So in this way you have calculated eigenvalues. As far as eigenvectors are concerned, we have already discussed in previous lectures. You have to, eigenvectors are non-specific values, and these can change according to the assumption of the constant k. So if you don't remember, you should follow the previous lectures. However, I have written the values of eigenvectors concerning to lambda 1 equal to minus 1, lambda 2 equal to minus 2, eigenvector is given by this, lambda 1, lambda 3 equal to minus 3, eigenvector is given by this expression. So in this way you have taken the eigenvalues and corresponding eigenvectors are calculated. Put these eigenvectors in columns and you would be getting the, this is your eigenvector number 1 according based on minus 1 eigenvalue, and this is eigenvector based on lambda 2 equal to minus 2, and it is eigenvector third which is based on eigenvalue 3, that is minus 3. So this is model matrix. So one aspect you have calculated, that is the model matrix. Lambda 1, lambda 2, lambda 3 you have calculated. Now next target is only that is remaining to get the inverse of this matrix. So you can simply calculate the inverse of this matrix M. Now I have written directly, and you can calculate by using pen and paper. So this is the value of M inverse. Now e raised to a bar t, it is e की power lambda 1t, e की power lambda 2t, e की power lambda 3t. Lambda 1 is minus 1, it is minus 2, it is minus 3. So it is easily written. Now the formula for state transition matrix, e की power at is equal to m into e की power a bar t into m inverse. So put the value of m, e raised to a bar t and m inverse, multiply all of the matrices, and finally you will be getting this response or this result, which is your state transition matrix using diagonalization method. So using diagonalization method, you have to simply have, you can keep the things in mind, like e at is equal to m e raised to a bar t m inverse. M is model matrix. E A bar T is the matrix which is having diagonal elements e raised to lambda 1t, e raised to lambda 2t, e raised to lambda 3t. So this is much easier to calculate diagonalization matrix. However, in case of illustrations, you will be finding some difficulties. Now, next aspect we are taking that if you are having a state model, then how state space model would be determined in terms of diagonalization or by using diagonalization method. So again, you have to take xt equal to mzt, in zt is the new state vector. So z dot t would be equal to this expression, xt equal to x dot t equal to axt plus but, x dot t would be equal to mz dot t. So mz dot t equal to a into xt, xt you have assumed as mzt, so a into m into zt plus b ut plus b ut. Similarly, by t equal to cxt, xt we have assumed as mzt, so it would be cmzt plus dut. So in this way, a new state model you got, that is z dot t equal to m inverse. Take this m from left to right, it would be m inverse am zt plus m inverse b into ut. Similarly, by t equal to cmzt plus dut. M is again the model matrix whose elements are determined by eigenvectors, and eigenvectors are in response of the eigenvalues. So now consider one example, numerical example, that is defined by x equal to 3, 4, 2, 1, x plus 0, 1, u. So this is your system matrix A, and this is B, and this matrix is C. So target is to calculate the value of model matrix. That is, initially we have to calculate the value of eigenvalues, and according to, on the basis of eigenvalues, you would be calculating the eigenvectors. So eigenvalues of this system can be given by the determinant of A minus lambda I equal to 0, and on solution you would be getting lambda 1 equal to minus 1, lambda 2 equal to 5. Once you got the values of eigenvalues, then you can calculate eigenvectors corresponding to these eigenvalues. So in one case we would be considering one eigenvalue, in another case we would be considering another eigenvalue. With respect to one eigenvalue, you would be getting one eigenvector. So initially we are taking lambda 1 equal to minus 1 eigenvalue, and let us assume this is eigenvector C1 whose elements are C11, C21. So according to the concept of eigenvector, this expression A minus lambda 1 I into C1 should be satisfied or equal to 0. This is the condition. So put the value of A, lambda 1 equal to minus 1, and I is the identity matrix C1, that is the eigenvector C1 corresponding to lambda 1 eigenvalue whose elements are C11, C21. Multiply, and you would be finding that this is the expression 4, 4, 2, 2, C11, C21 equal to 0. So on simply observing the matrix, you are getting that one of these rows can be made as equal to, all elements can be made as equal to 0 by just application of the row operation. So for here in this case a row operation, you can multiply these elements by 2 and then negate the row number 1. So row R2 can be replaced by 2 into R2 minus R1 and your element of row number 2 would be 0. So there would be only one equation, that is the 4C11 plus 4C21 equal to 0. By the concept C4C11 equal to minus 4C21 or C11 over 4 equal to minus C21 equal to divided by 4. 4 can be taken as common, so it would be C11 over 1 equal to minus C21 over 1 equal to, if we are considering a constant quantity k, then it would be equal to k, as we are doing in the case of calculation of the eigenvectors. So once you equate it to a constant k, then C11 equal to k and C21 equal to minus k. If you are considering k as 10, then C11 equal to 10, C21 equal to minus 10. If you are considering k as 1, then C11 equal to 1, C21 equal to minus 1. So the value of eigenvector corresponding to an eigenvalue basically based or depends on the value of k. So this eigenvector cannot be a specific quantity for an eigenvalue. It can be 10 minus 10, it can be 20 minus 20 or 500 minus 500. Ultimately, your eigenvector is having elements as 1 minus 1. So it is the general concept that it should be simpler values. So we have considered as k equal to 1 and the values are 1 minus 1. Similarly, for next or second eigenvalue, that is equal to I think 5. So lambda 2 is equal to 5. So now we have to calculate the value of eigenvector. If it is defined as C2 and its elements are C12, C32 for lambda 2 equal to 5, then again it should satisfy this condition, a minus lambda 2I into C2, the eigenvector equal to 0. So put the values, you would be getting that this is this expression minus 2, 4, 2, minus 4, C11, C21 equal to 0. Our aim is to simplify the expression. So one of the rows would be, elements of one of the rows may be kept as 0. So it is very much easy to make second row's elements by just a row operation, that R2 is replaced by R2 plus R1. So if you are applying this row operation, you would be getting this element as 0, this element as 0, and minus 2 and 4 are elements of the row number 1. Write your expression, it is minus 2 C12 plus 4 C22 equal to 0, or on simplification you can get C12 over 4 equal to C22 over 2. 2 is as common, so C12 over 2 equal to C22 over 1. Again this can be equal to a constant quantity k. So C12 equal to 2k, C22 equal to k. Assuming that k is equal to 1, we should assume a simpler value, so k can be assumed as 1. So C12 equal to 2 and C22 equal to 1. So your eigenvector is 2, 1 in case of C2. considering the eigenvalue as 5. So in this way you got two eigenvectors. By putting both of the vectors aside, we would be getting the model matrix M. So in this way you got the values of C1 and C2. So your your model matrix M is given by 1 minus 1 to 1. Right. For the calculation of M inverse, you can calculate by adjoint of M divided by the determinant of M. I have written directly. You can calculate by your pen and pencil or by using your calculator. A bar, it can be calculated by M inverse AM, which is the expression already derived. B bar, it is M inverse B, Cm like this. So your diagonalized state space model of non-diagonalized state space model would be Z dot T equal to M inverse AM ZT plus M inverse B UT. So this matrix would be a diagonal matrix whose elements would be eigenvalues of system A. So by putting the values of these one and getting the solution, you would be getting Z dot T equal to a matrix M inverse AM, result of M inverse AM, it is minus 1, 0, 0, 5. So these are the elements of diagonal matrix, and this is your first eigenvalue, this is your second eigenvalue into ZT plus 1 over 3 minus 2, 1, it is the value of B bar, and similarly for C bar. So this is your modified or diagonalized output, diagonal state equation, and this is your output equation of new system which is in diagonal form using diagonalization method. So this is all about diagonalization and use of diagonalization. So these are the references. You can also add the BC Kuo, Control System Engineering by BC Kuo, for referring. Thank you.